question, please send your question to bit.ly/GLS_Q&A and the link for the question list in the chat room as well. Or maybe you can ask directly by clicking the raise hand feature when the Q&A session starts. And today's GLS on SDGs will present the topic entitled Lab to Pilot Thermochemical Conversion of Biomass to Biofuel and Material through Green Processes, that will be delivered by Professor Suzana Yusup from University Teknologi Petronas. Other than that, we will also have a topic entitled Material Preparation and Separation of Useful Compounds of Microalgae, that will be delivered by Associate Professor Hidetaka Kawakita from Saga University. And this lecture will be moderated by Dr. Triyanda Gunawan from ITS. Before we start our agenda, allow me to deliver our schedule today as follows. So first, we will have an opening as we're doing now. Second, we have an introduction to moderator and speaker. And then we will have lecture session, and then Q&A session. Finally, certificate awarding and closing. Okay, now, before we proceed to the next agenda, let me introduce our moderator first. So, our moderator today is Dr. Triyanda Gunawan from Institut Teknologi 10 November. His educational background is he achieved his doctoral degree in chemistry, Institut Teknologi 10 November. On academic and professional experience, he has experience being a lecturer and researcher on Department of Chemistry, Institut Teknologi November, and as a secretary in Indonesian Chemical Society. And his research interest was in porous material, gas separation, surface adsorption, membrane science. Okay then, so that's a brief introduction about our moderator. Without further ado, let's proceed to the main agenda by Dr. Triyanda Gunawan. Okay, Ms. Triyanda, the time is yours.
Okay, thank you, Ms. Ocik, for your kind introduction. Good morning, good afternoon, everyone. Excellency, distinguished guests, ladies and gentlemen. Welcome to the quiz lecture series on Sustainable Development Goals. Today topics will relate to the affordable and clean energy, which is on the main goal of SDGs program, number 7. Excellencies, distinguished guests, ladies and gentlemen, among us, there are two outstanding speakers that will deliver about related topic. They are Prof. Suzana Yusup. Good afternoon, Prof. Suzana.
Afternoon. Oh, okay, let me share my video.
Okay, nice to meet you, Prof.
Hello.
Okay, and we also have Associate Professor Hidetaka Kawakita. Good afternoon, Sensei.
Good afternoon, guys. I enjoy my presentation, please. Thank you so much.
Okay, nice to meet you, Prof. Okay. And so before we start, I would like to read a brief CV about our distinguished speakers. So our first speakers, Prof. Suzana Yusup, will deliver a topic regarding the from lab to pilot, thermochemical conversion of biomass to biofuel and material through green process. Prof. Suzana got her PhD in chemical engineering in University of Bradford back in 2000. Her work experience, she is head and director of Higher Institution Center of Excellence of Center for Biofuel and Biochemical Research in University of Teknologi Petronas. She achieved numerous awards. Among them, she is listed in the world top 2% of scientists on single year back in 2019 in the area of energy, biotechnology, and enabling and strategic technology by Mendeley. And she also got Malaysia Research Star Award or MRSA back in 2019. Her expertise is in biomass conversion to fuel and biochemicals, material development, and green process. Our next speaker is Associate Professor Hidetaka Kawakita. He got his PhD in chemical engineering in Chiba University back in 2003. His research and professional experience, he is associate professor in Department of Chemistry and Applied Chemistry in Saga University. He is also have an experience in research associate in Kyushu Institute, Waseda Research Institute for Science and Engineering back in 2003 till 2004. He is also he was assistant professor in Department of Chemistry and Applied Chemistry in Saga University back in 2005 till 2009. He has numerous membership of academic society. Among them is the Chemical Engineering of Japan, Japan Society for Food Engineering, the Society for Biotechnology in Japan, and the others. His research interests related to the chemical engineering, separation, and reaction. So without further ado, we're gonna move to the next session, who is a lecture will be given by the Professor Suzana Yusup. Before I start, I would like to briefly explain the role of this session. Our speakers will verify their materials to all of us for about 40 minutes. And in the time being, all the participants can write question in Zoom chat or link that will be given by the committee. After that, we will have a direct Q&A session for 30 minutes. In that session, participants who have any inquiries can directly ask to the speaker by raising his or her hand first. Okay, maybe that's all. And Prof. Suzana Yusup, are you ready for today's sessions?
Yeah, thank you, Dr. Trianda, for the introductions. So allow me to share the screen. Yeah. So can you hear me well?
Yes.
Okay,
It's
so
clear.
do you get the visual now?
Yep.
Okay, okay. All right, so let me put it in the presentation mode. Okay, yeah.
Okay.
All right. Okay. Right. So first and foremost, thank you to the organizers for inviting me to share about our research work, related to thermochemical conversions of biomass to biofuel and materials. So what I'm sharing here is also, I was made informed this is to, give and impart knowledge to the students regarding how we can shift the findings in the lab to higher upscaling versions of the research. So with this in mind, so these are the expected learning outcomes. So I hope by the end of today's sessions, students will have a view how they can interlink between the SDGs, Sustainable Development Goals, with regards to research in the area of biomass conversions to biofuel and products. And from there, I will try to link up, when we do the process development, how we can link this approach to the process intensifications, where optimizations of the process, identifications of the key parameters is important so that we can optimize our research findings. And with this, I hope the students will also can integrate this SDG and the process intensification approach. And I will share also our research with regards to this topic. So these are the plan from today's engagement. Right. So if you see, when we talk about Sustainable Development Goal, with regards to SDG 7, right? So it is linked up with the affordable and clean energy. So here, this aspect of the SDG, we can integrate with the aspects of how we can develop a process or innovate in a manner that it helps to induce more energy conversion, higher conversions. Yeah? At the same time, it helps to improve the efficiencies of the overall process, right? So from this angle, it can be linked back to the sustainability and also the motions of diversifications of types of future fuels, right? From the renewability angle. And my view is that the SDG alone, it need to also be supporting other elements so that we can have a holistic view with regards to the approach of SDG, with regards to the responsible consumptions and production. Also, the impact can be linked, how it can also help to reduce this climate change issues that need to be mitigated. And from the developments of the technologies, it can also spur a step ahead in terms of entrepreneurships, right? Through the upscaling of the findings from lab to the higher level. And with this regard, we hope that it will also increase more SME, small medium industry, to be involved in the technologies where be able to convert conversions of biomass to produce products and also renewable fuels. And this can be achieved towards efficient partnerships to get this holistic target, right? And when we talk about SDG, it can also be mapped and translate against the 12 principles of green chemistry, in which this will provide the backbone or the initiative where we can link up when we do the research to have in mind that how it can help to reduce and eliminate the generations of hazardous substance from the design, manufacture, and applications of the developed product. So this will be the backbone or the standing, how we can map against the research towards SDG and moving forward with the 12 green principles. All right. And when we talk about energy transitions, right, we can see the biofuel here from the given chart is that it can be increased because right now, as we know, the most of the fractions is we are heavily depend upon fossil fuel, and then these conversions or tapping against waste, especially from the agricultural waste, municipal waste to produce biofuel, it also can help to complement the overall types of energy that can be generated from waste. At the same time, it can help to prolong the resources that we have through these diversifications and applications of various types of fuels. Right. And when we link up the holistic view from the big pictures where our research to be mapped against and support the SDG and embed the 12 principles of green chemistry and link it back with the process conversions here. There's various types of biomass, especially from the second generations biofuel, where the origin of the biomass comes from non-edible resources, right? So we can see now how the research worldwide is shifting from utilizing the edible resources to non-edible, such as the lignocellulosic waste that can be tapped and converted to produce various types of energies, such as a solid fuel, liquid fuel, or gaseous fuel, right? And further, the algae also is another third generations of biofuel that can be derived from it through various types of thermal conversions that can be applied, as also from the bioprocess route there. So in all, if you see from the shared slide here, there are various conversions route that can be introduced to convert the waste to energy and also to make a product, other types of products, right? So among the thermal chemical conversion technologies, these include the transesterifications, hydrogenations, and also gasifications, pyrolysis, right? And when we talk about conversions of municipal waste, it can be through anaerobic or aerobic digestions. It can be converted to produce various types of fuels, such as biomethane and also biohydrogen. So all in all, the important thing is that when we try to link up between technologies and the products that we want to generate, knowing the characteristics of the biomass itself is very important. Then from there, we can understand how much we can tap along and leverage on the calorific values of the biomass to produce, to be utilized in energy, to support the energy utilizations. So this can be in form of the heat, or it can be converted through mechanical process as well at the downstream here to produce the electricity, right? Now, so as I mentioned here, when we talk about biomass, so various types of biomass resources we can tap along to produce value-added materials as well as fuel. These can be leveraged upon conversions of municipal waste, examples that you can recover the food waste from there, and also industrial waste such as the sawdust or the residues from the examples, the coconut shells, from the rice husks, from the plantations of the palm tree there. So all these have great potentials that can be tapped to convert to fuel. At the same time, it helps to mitigate the issues or it helps to reduce the impact towards the environmental, right? And when we talk about the virgin biomass examples, the algae, depends on the type of algae there. It can also be converted to biofuels such as biodiesel, as an example. So all these residues and from the crops, it with a proper couple with the technologies, we can make a useful material from them, right? And as mentioned here, as examples, Malaysia and Indonesia very much into the oil palm fronds, and these are the residues that can be tapped upon, empty fruit bunch, palm kernel shell, old palm trunks, and the residue from, after paddy has been processed there. You can have the husks and also the rice straws. So all these waste can be processed to meet and to produce depends on materials of fuels for the target applications. Now, having known the status of this, let us link back. What is the process intensifications, right? So when we talk about process intensifications here, it can be linked up with the target capacity. Examples, especially when you're handling a process where the condition is involving with high pressures, right? So there's an alternative to be considered, that can this be mitigated through designing or using equipment that is very less volume intensity, so at the same time produce the product or the materials that we want, right? So in this case, process intensification also, it will provide an opportunities where we can maximize the energy consumptions. At the same time, when it coupled up with the waste utilizations, it can produce or offer a cheaper production cost, right? And this concept is not new. It has been applied way back in 1970 when Colin Renshaw and his colleague at the ICI in UK, they aim to reduce the capital costs associated with their plant installations. So these are the concepts where they try to reduce the footprints of the unit operations, and at the same time, and options of integrations of the equipment function is also being considered there. So now we know that we have the resources, the biomass, and then in terms of the process developments, through process intensifications and optimizations. So this approach can be coupled to produce or reduce the cost of productions, right? And these are some of the problems that we can think of when we want to, when we want to advance the research labs findings towards commercialization. So among others, right, amongst the things that we need to also consider, because as we know that when we do the findings in the lab, right, we need to also think about what are the potential design constraints that we need to consider based on not only internal factors. Internal factors can be in terms of the optimizations approach of the process development, but the external factors can be an examples, the legislation part of it, say that examples, if you plan to upscale the technologies, what about the taxations, right? And also site locality. So these are other amongst points that need to be considered when we want to bridge the gap between the lab towards the commercializations, right? And then among others also, what are the steps in the holistic view of the process design, right? So examples to have the steps in the process is important. So this, from the chemical engineering approach, we can do a simulation studies using HISIS or Aspen, where each types of unit operations involved, we can optimize and start predicting the potentials, productions, and also the how the overall process performance when all the unit operations is being integrated. So the key points is that we need to have a holistic view from the design constraint itself, and also from what are the steps that that will be involved when we try to upscale the technologies, and how the the documentations when we want to upscale the findings from the lab to the pilot scale. And another thing, among others, is what about the codes or standards, registrations that we have to abide? Examples, from the environmental perspective or from the safety approvals that we need to conduct, right? And further, there's also decisions that need to be taken care of, whether, okay, is it a batch process or a continuous process? So this will very much depend upon the cost, the production cost, and the nature of the products that need to be synthesized, right? And these are among other points of wonder when we try to advance the findings in the lab research towards commercializations, right? So in linking with that, there's some other points here I've listed here, where the overall view in terms of resources and the demand, supply and demand, need also to be looked into, which is very much linked to the market size and also the utilities, the requirement, the how much energy need to be needed to upscale the technologies, and also the compatibility of the technologies and the sites locations, as well as the utilities point of view, and the transportations, and what happens if now you have produced your product, right, in a bigger throughput there. So how it need to be shipped off to the respective places. So this is where the all these external point and the point of view from the supply chain, as well as the support, the utilities, the surrounding area need to be considered. What about the labor supply? What about the disposal if the technologies is being upscaled in a larger volume capacity? And what about the taxizations and legal restrictions? And will the site selections have any impact towards the stability and also the community factors? So these are among others points that we can think of when we want to start linking how to push the findings from the lab towards commercializations, right? So when we look at these elements, so it can be approached. This is Sham's sharing to the students here. So in moving the research findings, it can be the questions that we can think of at the front end is that, can we do this by modifications, or can we do some tweak to improve to the existing plant? Okay, if that productions already have the plant there, is there any remediations or modifications to the existing plant, or do you want to develop a totally new production capacity, right? But this need to be also tackled from the angle of the demand side, right? And then, or totally, you are pushing the research findings from the lab to the pilot to the commercializations. This is where the integrations, process intensifications, process integration approach can be considered, right? Now, so linking up with the topics, okay, I'll talk about the SDG, and green chemistry, the 12 principles of green chemistry. And I've shared upon the process intensifications and what are the factors that we can map against or make ourselves ready when we want to push our research findings to commercializations, right? So now I would like to link it up with our research that we have done here. So one of the technologies that we developed is known as the hydrodynamic cavitations technology, where we before we do this pilot plant or scale up, we have started with a lab analysis in a small scale first, and then from there we do the analysis in terms of the feasibility studies, right? Lab proof of concept, how much of the conversions or the yield that we will get before we start upscaling our research finding. And from this research work, we have tried with various types of biomass, especially we've tried with the non-edible resources, such as the waste cooking oil, and then we have tried also, to test the robustness of these technologies using rubber seed oil, and then to get the biodiesels, which is methyl esters base, using these findings that we have started from the lab to the pilot, right? So just to let the student some insights how this system works. So these technologies, because if we look at the current standing in terms of the productions of biodiesels, is very much, I think, the cost is associated with the production cost itself, right? So the question is that how can we minimize these energy utilizations? Can we do some improvement in terms of the rate of conversions from the feedstock to the product side? So through these technologies, what we find out that yes, we managed to increase the rate of conversions of our feedstock, and then to produce the product of our interest within 20 minutes, as opposed to the conventional approach. It takes more than that, right? So from these findings, it shows that hydrodynamic cavitation technologies have a potential to convert various types of biomass feedstocks, especially in the liquid form, to produce the biodiesels, right? So how does it works? Here we tap upon the mixing through the cavitations, formations of these bubbles, vapor, and then from here it will enhance the interfacial context between the oil and the methanol. Then we get a good mixings there, and then at the same time it will help to improve the conversion process. Right. So in our second technologies that we have developed, linking up with the thermal chemical conversions is where we explore various types of biomass waste and through the utilizations of CO2, we try to do the CO2 activations because in our mind that we are testing the hypothesis of can we utilize the CO2 at the same time produce a better quality of activated carbon. So this is another approach where we try to optimize our process conditions to find to make value added product from biomass waste, right? So here it shows that it gives an encouraging findings to us because we have tried with various types of precursors and also biomass types, so we get the target activated carbon of our interest. So this activated carbon, it has many applications that it can be applied, to treat water in water purifications, as well as it can be, used for the soil enhancement, where this will also support the growth of plants, and then with hoping that it will still contribute and linking up again to the SDG. All right. So another types of system that we develop here is known as the catalytic steam gasifications. So with the for this technology also, we start from a lab scale where we do the analysis and feasibility study in small grams before we go to this pilot, where we test our hypothesis if we use various types of agricultural waste, and then we couple against using the various types of catalyst and also activated calcium oxide, right, the adsorbent, if this will help to enhance hydrogen production. So these are another technologies that it helps us to prove the concepts that yes, you can convert biomass to green hydrogens through this catalytic conversions approach using steams as the one of the diluent there, right? Now, I think I have a few more minutes here. Okay, one of another technologies that I want to share, is the potentials of utilizing CO2, where we can extract various types of chemicals, chemical compound. In this case, we upgrade and upscale the quality of the biooils that we produce through this supercritical fluid extraction. So this is where the process optimizations has been done, where we try to find what is the best conditions that give us the target quality of the biooils that we want, right? So we do this to extract the phenolics compositions, among within this crude biooil there, so that we can upscale these findings to make a value-added product, right? Now, another examples here where we are aiming and we still utilize the CO2 through the supercritical fluid extractions, where we try to find what are the bioactive compounds that we can generate from extracting various type of plants material. Examples, the papaya leaf, the Melaleuca kachiputi. If that extractions can give us the compound of our interest. Examples, humulene that is active ingredients in bioherbicides, so that it will help to suppress the growth of paddy weeds, right? So these are among other technologies that we have explored as well. All right, and further results can be found in our publications here if need further informations, right? I think these are another one of the technologies that I want to share with the students here, is that through applications of microwave assisted technology here, where we can produce a greener solvent, this solvent can be used to denify the biomass. So one of the application is that it can help to offer an alternative approach in the pulp and paper industry, where we can have a greener solvent and an alternative approach, so that the overall process is become green. Yeah. Okay. Right. So linking out with this another of our work, when we link up with the biofuel productions as well. So as I mentioned, in one of the elements of process intensifications there, the cost reduction is important, right? So in one of our work where we need to reduce the overall production cost, especially in the catalytic hydroprocessing. So this is where we start to find alternative solvents in the questions of, can we crack our feedstocks to produce a green-like fuel by using tetraline, so that it can generate the hydrogens in situ, rather than we have an external supply of hydrogen. So all in all, I think this is the last case study I want to share with the students, that from this, I hope the students another learning outcome, that to have a holistic view of the processes when you want to link up with the lab towards towards the higher pilot plant productions. The life cycle assessment is very important, so that we can have analysis what are the environmental impacts that associated with the process that you want to develop there, right? So in here we have done in one of our work where we do the extractions of oil from this waste of this plant here, and then we do this LCA analysis, right? So the approach that we have taken here for the LCA analysis is more on the gate-to-gate analysis, where we try to analyze what are the sequences if we have various types of energy resources that we use to support these applications of extractions of essential oil from this plant, right? So our finding shows that yes, that there's a difference when you use different types of energy resources, fossil-based versus renewable resources there. So the global warming potential also is reduced when renewable energy is being used as a electricity source to support the overall process of extractions, right? So with this sharing, so I hope that the student, the learning outcome, that the student will get here is that, through SDG green chemistry, you can link up the approach there with the process integrations, and this can be observed through applications of waste utilizations. In these case studies, I've shown how you can use CO2 there as a means to extract the value-added materials, and also use biomass waste to produce products such as activated carbons and also biofuel there, right? So at the end of the day, the SIG is moving towards a cost reductions, and at the same time we be able to increase the overall process efficiencies, right? So allow me to, I'd like to express my gratitude to all my students, my universities, and my colleagues, the peoples that be with me, especially my students, graduate students, in doing the research up to not only from the lab level, but we are moving towards lab pilot level. So with this, I would like to thank you, and I open for any Q&A questions. Thank you.
Right. Thank you very much, Prof. Suzana Yusup. Actually, you still have 10 more minutes.
Oh, okay. I thought sorry for that, because yeah.
Okay. Okay, well, that is a very insightful speech and presentation. I also learned a lot from your presentation, Prof. Yusup. Thank you for sharing to us. And without further ado, we will move to the next speaker, Associate Professor Hidetaka Kawakita. afternoon, Sensei.
Okay, I will
Okay, are you
share.
ready?
Yes, I'm ready.
Okay, thank you. So
I'll start
the screen
sharing.
is yours.
Okay.
No.
Can you hear it? Can you?
Yes.
Okay. So thank you. Oh, sorry. So thank you for introducing me. And I am Hidetaka Kawakita from Saga University, Japan. And firstly, I'm very thanks for the committee member of the GLS. And I'm much pleasure to have a presentation here. And my title is Material Preparation and Separation of Useful Compounds from Microalgae. So firstly, I'd like to introduce my university, Saga University. This is a public university. And this is a picture of the entrance. And this is Tokyo. And Saga University is here, just far 2 hours by airplane. And Saga Prefecture is here. And do you know the Fukuoka? This is Fukuoka. And 1.5 hours by bus, very nearby. So if you have a chance, please come to Saga University. And my university has 1, 2, 3, 4, 5, 6 faculty: education and region, design, economics, medicine, science and engineering, and agriculture. So in Japan, the size of the Saga University is very small. So we can have a much communication with the students as well as the professors. Okay, I'd like to introduce myself. And my major is chemical engineering. And I already got some degree from this university. And chemical engineering is including separation, reaction, and they should be combined for process engineering. So the professor, as Professor Suzana said, that the process intensification is much important as well. And in the chemical engineering, some chemical should be produced for the application of the food cell or some fuel or everything. So we can enjoy chemical engineering very much as a professor. So my research is much complicated and much separated. And here is a part of my research. And this is a particle separation using compacted gel layer. And here is a gel and spherical gel. And spherical gel is packed in the column. And some size of the colloidal particle is inserted here, and water is permeated. And at the bottom of the gel is very compacted. Here is a picture. This means that in this area, pore of among the gel is very small compared with the top one. So in this system, we can separate the colloidal particle that is depend on the size. And this is also for the particle separation by the hydrodynamic chromatography. And this is a very popular fluid velocity profile as a Hagen-Poiseuille profile. And center is a very high speed, and the edge is stopped by the wall. And if some particle is injected here, larger particle will be eluted faster. This is a 1 micrometer particle is fastly eluted, and 20 micrometer particle will be lately eluted. At this time, the particle will be possibly separated. And this is the metal recovery. So I mean the separation of the and recovery of the palladium particle. And palladium particle is dispersed in the viscous solution of the polymer, and some polymer is added here. And then the particle is captured by the polymer and then precipitated. At that time, the nanoparticle can be recovered perfectly. And this is just like, I mean, the modification of the porous membrane with the colloidal particle. This is applicable for the particle separation and protein separation and so on. And this is the dioxin treatment degradation by CSTR and stripping column system. Stripping column is just like a distillation column. And this is the particle separation along with the magnetic field application. And in this case, the particle has a magnetite here. So if the magnetic field is applied to the column, the gel sphere will be moving in the column. So the colloidal particle is eluted slowly and slowly by the moving dynamic gel layer. And also this is just like a enzyme immobilized magnetite by the application of magnetic field in the plug flow. So this is a continuous production process for especially for the polyphenol. This is very much interested in the world now. So anyway, my talk today is the engineering of the microalgae. So as you know, the microalgae has a much potential for the material, biofuel, cosmetic, bioplastic, biopolymer, and pharmaceuticals. And also the world is focusing on the immobilization of the CO2. So actually the circular, as you know, circular economy's idea is much popular in the world. This means that the recycling, production, utilization, and this circle will be just rotating. And some feed, if the some feed is added to this circle will be again started rotating. Recycle, production, utilization. And this circular economy is much interesting for especially for the local region in the Saga city, Japan. So to improve the engineering of the microalgae in Saga University, we have a team for the professors. And he is a vice president, and he is an agriculture professor. This is I. This is a team of the science and engineering, and he is a professor of the medical. And he is also head of this team, Professor Demura. And he controls everything because he is a professional of the microalgae. And we can make some plan. That means that the Saga city is population is like this, and key technology, key industry is agriculture. So we have a lot of biomass, and we have this kind of the large scale garbage incinerator. So CO2 is generated, but how to use the CO2? That is a problem. So to make a circular economy, we should use the CO2 efficiently. At that time, microalgae is a key plant to use the CO2. So in our team, we have a kind of flow for the research. First one is the cultivation of the microalgae, and that is broken by some technology, and the microalgae is used for the fertilizer, and some pharmaceutical is extracted from the microalgae. And the microalgae has a lot of polymer, and that will be separated by me, and these are applied for the medical. This is a kind of flow for the treatment of the microalgae in our university. So this is the Professor Demura's research is that he is good at cultivation of the microalgae. So microalgae is very spread in the world. There are a lot of species. So that means that the Saga has a typical species of the microalgae. So I think in every area, every microalgae are there. And in this talk, I want to talk about the separation material from microalgae. And in this study, the harvesting by the microfiltration membrane and magnetite, and the extraction of the protein by ultrafiltration membrane, and the microalgae is applied for the fiber, and the waste of the microalgae is applied for the metal as solvent. So the first is the microalgae and solid liquid separation for the harvesting. Here is the microalgae structure. And this is a lot of application for the biomass energy, pharmaceuticals, and additive food. And how to separate the microalgae after the cultivation is one of the problems. That should be efficiently. So at that time, we use the membrane. But the important thing is that how to overcome the reduced flux due to foulant. I mean that during the filtration, some protein and some chemical is fouled. I mean, just like a cake layer to stop the flow through the membrane. That is a critical point. So we should overcome it. So here is the structure of the porous flow fiber membrane. Actually, this is always applied for the pure water obtaining. And this is the structure of the cross flow. So here is the pore. And this structure is much complicated. Please see the Google to see the exact structure. You can easily find it. And here is the pore, and here is the flow. And during the filtration started on the membrane surface, but the cross flow to the Z direction takes place. At that time, cross flow generates the shear stress to sweep cake layer. So the thickness of the cake layer will be thinner, and then the flux will be higher. So in the case of the microalgae is a kind of gel, spherical gel, because the microalgae has a lot of water in their body. So the compaction of the cake layer occurs to reduce flux. This is a serious problem. To overcome it, we add the filter aids. I mean, without the filter aids, the microalgae is compacted like a ball. So the pore of the membrane will be stopped to lower flux. But if we add the filter aids like this, here is the water path. So we can enhance the flux. So porous flow fiber membrane plus filter aids will be much high ability for the higher flux. So we use the magnetite. Magnetite can be recovered by the magnet easily. So after the filtration and dewatering, the magnetite can be easily recovered by the application of the magnet, and this is a concentrated microalgae will be obtained. Here is a illustrated structure of the equipment. Here is a porous membrane, and here is a microalgae suspension, and this is just like a circulating like this, and some water is out from the membrane. So this is the structure of the nanocropsis sp species, a kind of the microalgae. And here is the structure of the porous fiber membrane. This is obtained from the Assoc Kogyo in Japan manufacturer. And we as a magnetite to here and start the dewatering. And then we change the concentration, the magnetite added as a function here, the microalgae and magnetite. In conclusion, here is the flux. So K is the flux reduction coefficient. This means that the lower is the better. Lower K means a higher flux. So here is a higher flux obtained. This means that the number of the magnetite against the microalgae should be optimized to get the higher flux through the membrane. And as I already mentioned before, that after the dewatering with the membrane, the particle will be easily recovered by the flowing system. And this is the before separation. We can see the magnetite here, but after the field separation with the magnet, we can recover the magnetite easily. So next, I'll explain the extraction and purification of the Ficobil protein by ultrafiltration membrane. In this system, we can purify the protein by the stepwise ultrafiltration. So Ficobil protein is a kind of the colored protein. And this is really expensive, so we can get it for the industry. We want to apply this one for the medical field or the fluorescence for the analytical field. And firstly, we should extract Ficobil protein with from the Gnostic commune here. This is a kind of the microalgae. And freeze and thaw method is a very powerful to extract the Ficobil protein. And this is a solution. And after the ammonia sulfate treatment, we can get the much concentrated Ficobil protein like this. And unfortunately, this solution still has a lot of biopolymers coexistence with the Ficobil protein. So we should separate Ficobil protein from here. And our idea is firstly, larger pore membrane is through this solution and the stepwise UF treatment. And then we can get the concentrated Ficobil protein. Unfortunately, the steps is not here, but we can try it now. So the system is similar to the previous one. And the Ficobil protein is here. And the solution is circulated like this. And some solution is out from the membrane. So number 2, protein concentration will be higher because some solution is out from this. So to consider this system, we should make, wow, are you okay?
Yes.
Okay.
Fine.
So, okay. Okay, congratulations. So, oh my God, okay, so sorry. So this is a membrane system and protein is concentrated here because some water is out from the membrane and some chemical is out from the membrane. At this time, this structure should be considered. I mean, here is a membrane structure and some protein is just like fouled as a cake layer. Cake means just like a cake for Christmas or cake for the happy birthday. we usually use it. This is just like a cake structure. And at that time, cross flow is applied just like a Z direction. So shear stress is applied to sweep the cake layer. And so we step the membrane is a much familiar technique at present. And here is a various species, and that is dependent on the application. So microfiltration has a pore like this. So this is applied for the cells and microorganism separation I already mentioned before. And ultrafiltration pore is like 5 nanometer. So this is much applicable for the purification of the protein, DNA and RNA, and nanofiltration and reverse osmosis membrane is much familiar for the desalting of the sea water. We always use it. So anyway, our target is a protein, so we use the ultrafiltration membrane. So this is a extracted Hikobi protein containing solution, and this is a picture of the solution, and this is a GPC, gel permeation chromatography. So this is a commercially available hicocyanine, a kind of Hikobi protein, and this is a target protein peak. And also there are some biopolymers. So we can get this one to be concentrated. And this is a UV-based spectrum. And if the concentration is changed, especially this is a colored peak of the Hikobi protein. So we should concentrate the protein for the focusing this one and this peak, actually. So, okay, I start the purification of the protein solution, and this is a flux, and this is a concentration protein, the effluent. Actually, so the detail is not uncertain, but if the time is started, the flux will be declined because the cake layer is formed on the membrane surface. But the cross flow is very effective to sweep the cake layer, so the flux will be reached at the steady state. And the concentration of the protein in the effluent will be gradually increased. And higher pressure will be better because some compaction will be occurred. Okay, so here is a gel permeation chromatography's peak. As you see, this is the original one. Here is a very small peak, but after the concentration, we can get the high concentrated peak of the Hikobi protein. But unfortunately, from the UV beads, the purity is less. So this should be more treated with the ultrafiltration treatment. Okay, from here we can use a mathematics for the use of the cause. I'm chemical engineer, so I want use a mathematics to make some mathematical model that is applicable for the understanding of the phenomena of the cake layer, as well as this one is applied for the process engineering or the scale up. So here is a cake structure, and this is membrane, and cake thickness will be increased with starting the permeation time. But the cross flow is very effective to cut the cake layer. So thickness will be reached at the steady state. And some protein will go through the membrane to go out. So this phenomenon is described by some mathematics. The first one is we set the max thickness of the cake layer. And K1, K2, K3, K4, and K5 is a parameter. And this one is related to the Reynolds number. And flux is described by the equation 2. And permeation resistance of the flow is described using this one. And cake formation is described number 4. Because the cake thickness L is a time dependency. And this is the ordinary differential equation. And also the concentration change of the feed here is described by the equation 5, and concentration change in the effluent here is described number 6. So we can describe the phenomena by 1, 2, 3, 4, 5, 6 equations. And this line is fitted line. The equation is analyzed by the Runge-Kutta equations. So fourth order Runge-Kutta equations. And the parameter K1 to K5 will be obtained to understand the phenomena of the cake layer and to find plant scale process composed membranes. Okay, this is a picture of the pressure dependencies on K3 and K4 and K5. And this is also pressure dependence of K3 and K4 and K5. I skipped the detailed explanation, but in the case of the higher pore, the membrane is formed like a cake layer. But in the case of the smaller pore, the clogging of the pore by protein occurs. They are obtained from the information of the K3, K4, and K5. Okay, I see. Okay, so next I'd like to explain the use for the metal as solvent, this one. So rare metal is very expensive, so we can get this one, gold, platinum, and palladium are so solid, so the unit is yen, but this is much expensive. So we can get these precious metal. And in this case, the useful metal is just like I said, the recovery, but the toxic metal is called as a removal. That's a little bit different. And urban mine is metals in the city. We always use a lot of metals, especially for this kind of the computer or mobile phone also. And after use up, they are just like a trash. But trash has a lot of metals, so we should gather some PC, and from that we can get some metals. At that time, we should separate the metals. So this is the work by the Professor Keisuke Oto, because we are the team of the treatment of the microalgae. And this is so microalgae, after usage of the microalgae is treated with H2SO4 to make just like a adsorbent. So this is the data for the selective adsorption of the gold. And if treated with the sulfuric acid, gold can be recovered perfectly. X is the concentration of the HCl, because the HCl is always used for the dissolution of the metal from the PC. And as you see, we can see the gold particle like this. Because in solution, Au has a structure of the ion, but ion is reduced to gold, and gold is started to form a particle, just like a crystallization. And also we can check the structure by the XRD, and we can see the Au0 peaks. So we can selectively get the gold from the metal containing solution. And we want to apply this one for the continuous mode. And this is just like a labo scale experiment. This is just like a plug flow continuous mode. And this is a column. And here's a pump. And metal containing solution is permeated through the column. And some metal is selectively absorbed to the column. And the concentration C will be changed gradually. This is a breakthrough curve. Do you know? X is a permeation volume, and Y is the concentration ratio between the concentration in the effluent and initial concentration. So metal is gradually absorbed and stop the absorption, and the concentration will be same as the start one. This is called as a breakthrough curve. And our idea is that we should be a rich code. So target should be precious metals, Au, Pt, and Pd. Also, copper, nickel, and zinc are also included in the waste of the PC. But they is not, unfortunately, expensive, not expensive. So our target firstly should be set to the precious metals. And here is the firstly, the column selective for the Au is packed here. And then next, this is a kind not related to the microalgae, but some waste paper, my adsorbent is packed here. Then some precious metal containing solution is permeated through here. At this time, we can firstly get the gold. And then next, we can get the platinum and palladium selectively. This is the first data. And in the metal solution, there are a lot of species of the metal. And this is a breakthrough curve. So gold, only gold, gradually absorbed to the column. And the other metal are not, unfortunately. So we can get selectively gold. And the other platinum and palladium were containing in the effluent. I mean, gold is selectively to this column, and the other metal is included here. And next, we started that this solution is go through the column, next column. And then gold is already gone to the first column. So palladium and platinum can be get like this. And the other copper, zinc, and iron will go through the column. So we can get the precious metal selectively. But unfortunately, so after the absorption, we can get the concentrated metal ion. So we should recover the metal ion from the column. So to recover the gold, 0.1 molar HCl plus 0.15 molar thiourea solution is permeated. So gold can be selectively eluted. So we can get the concentrated gold. And then we next permeated this solution to the second column. So we can get the palladium, platinum selectively. So we can be rich. So microalgae has some potential for the metal recovery because this has biopolymers of cellulose, protein, and so on. And this should be modified chemically for the high variable material. I mean, the utilization of the biomass microalgae. And this is applied for the urban mining, and they should be viewed by the political and economical to overcome the economical problem. So as the previous presentation, Professor Suzana said that process intensification is much important to make more real engineering. So next one is a microalgae fiber preparation. And this work is by the Professor Takayuki Narita. So he used the electrospinning process to make a fiber. So here is a solution of the polyvinyl alcohol. This is a polymer solution, and polymer solution is mixed with a microalgae, broken mixed microalgae. And this solution is added here. And the fiber preparation is started. And we can get the several fiber diameter like this. This is the concentration of the PVA is like this. We can get the very small diameter fiber, but if the concentration of the polymer is higher, here is a very wide diameter. And actually, some bulk microalgae is included here. So this can be used for the, this is a mask, but this is applicable for the filter, especially for the microalgae including filter. This is much applicable for the, light, because the microalgae has the CO2, the ability of the CO2 immobilization. During that, the light from the sun is used for the some energy by the microalgae. So this kind of the fiber, including microalgae, has a much application. We have a much application for the much more smart engineering idea, I think. Okay, so hopefully my idea is that here is the idea again. Here is the idea of the circular economy and recycle production and utilization. And as I said, the microalgae has a composed of the biopolymer and including a lot of polymers. So this one should be more used using a rotation. And this system should be set as a local area, especially Saga. Saga is a very local area in Japan, different from Tokyo. So, but we have a chance to set this kind of the idea in the local region, I think. So finally, I acknowledge to the professors and committee members of the ITS and committee members of the GLS. And I thanks to the Masato Tominaga, Professor Masato Tominaga, Saga University. He introduced me to have a presentation here. Very much thank you for this kind of invitation. Thank you so much. Thank you very much. That's all.
Okay, thank you very much, Sensei Kawakita. Actually, you still have 2 minutes left for your presentation.
Okay, so yeah, it's over. So thank you so much.
Okay, a very interesting speech about microalgae, a very small objects that hold a very huge application potential. Thank you. So that's it all for our speakers presentation. If the participant have any question, you can ask directly to them by raise your hand feature. Or maybe I will start first. I have some question to our speakers. The first is question for Prof. Suzana. Prof. Suzana, you have an interesting lecture series regarding the from lab to pilot scale. And actually in our research group, we are trying to do that, and we have a dream to have our own pilots, maybe laboratory. If based on your experience, what is the main challenge or for fundamental research that can be brought to the pilot scale? And again, from your best of experience, when do you think our research are ready to be applied in the pilot or larger scale? Thank you.
Okay, thank you for the interesting question, Dr. Trianda. Yeah, so I guess like once, for my view, once we have found your confirmations, proof of concept, at the lab scale, then in moving towards the pilot, you need to have a holistic process assessment. Yeah, so process assessment, this is where you start outlining, you know, the supply, the demand, the operating conditions, right? So the points that I shared just now with the constraint, the internal, external factors, right? So a process plant approach, this is where the work together with the process engineers, chemical engineers, right? Because my view in moving towards lab to pilot is multidisciplinary. Then you can have all these, expert advice and insights, to get to ensure that when you have upskill it can work, at least from my experience, like, okay, there will be deviations, right? Examples in lab scale, because the lab is the ideal situations, right?
Yep.
So when you push to the pilot, there's some deviation in terms of the boundary limits of the optimization conditions. But at least from there, once you have found where the boundary is, fall within the limits when you upscale, then this is where you do your commissioning optimization again. So in a way that it is not like a straight path, it has to be reiterate, recommissioning, then you get a different learning. But the knowledge that you experience in fundamentals is very useful to help you out when you start to upscale. So yeah, so I hope it answers your questions there. Yeah.
Okay, thank you very much. Because we have a doubt, is our research is ready or not? So it just end up in the journal or in the script or something like that. Okay, thank you very much, Prof. Suzana. And I also have a question for Associate Professor Kawakita. Prof, I'm interested in the rare metal adsorption. You say that microalgae, if we are treated it right with the, if I'm not mistaken, sulfuric acid or hydrochloric acid, it can absorb to some metals. For instance, is gold.
Yeah.
I'm curious, what is your a sample? I mean, the fits that to be absorbed by the microalgae. What is where does it come from? Is it from a treated waste or something like that?
Yeah. If the actually, so we have a lot of waste in your country also that is composed of biopolymer. So that is applicable for the adsorption of the metal ion. So Professor Suzana also said that you also use a lot of biopolymer. So that's also used for the metal adsorbent, I guess. Treated with the H2SO4, and then that is applied for the, especially for the precious metal recovery. Okay. If you want, please, yeah.
I see. So the precious metal recovery is coming from the waste of the electronic, or or how you treated the waste of the electronic? We treated it first?
Yeah, there are a lot of ways to reach the metal ion from the PC circuit board, because the circuit board is firstly made of the plastic, and on the plastic board, some metal ion is just like inserted, like a integrated circuit, or like there. And then the powerful one is cyanide. Cyanide, yeah, cyanide is first, but very dangerous. So we want to skip it, and HCl is the second candidate for the reaching of the metal ion. And yes, but a little bit dangerous, but you can get some metal ion, precious metal ion, by treated with HCl.
Okay, I see. Okay, thank you very much, Associate Professor Kawakita.
Thank you.
And here we have two questions for our participants. This one is addressed to Associate Professor Kawakita.
Yes.
From Aulia Ulfah. She is from Environmental Engineering. She has two questions. The first question is, how is the operational for the membrane that clogging because of the microalgae? Do you wash do you wash manually the membrane? I mean, if you got your membrane fault by the microalgae during the harvesting, what
You
is the
mean
best treatment to recover our membrane?
yes, yes, yes. So you mean that during the filtration, some microalgae is filtered on the membrane surface.
Yep.
So you mean that some cake layered microalgae should be recovered also. Yes, so at that time, the two ways are candidate. The first one is the cross flow rate should be higher. I mean, the Z direction flow should be higher. And the second way is a backwash.
Oh, backwash. Okay.
Backwash. You are good at membrane technology. So backwash is but during the filtration, dewatering, the concentrated microalgae are obtained. So the cake layers microalgae are less compared with the feed concentrated microalgae.
Yeah.
Yeah, it's just a really complicated system, but yes, that's it.
Okay, so we do the operation is accessible in the cross flow process, and as well we can use backwash filtration, right?
Yeah.
Okay.
If you want.
Okay. Okay. So the second question is how to determine the optimum pressure in different membrane.
Okay. So actually, so that is a good question. So the membrane are generally composed of the ceramics or the polymers, polysulfone or polyethylene or PDMS, or there are a lot of composed of polymer. At present, the scientific view of the interaction with the membrane and target ion, target polymer are not cleared, not yet. So in this time, we should firstly make an experiment. No model, no mathematical model of to clear the phenomena, unfortunately.
Okay.
Yeah.
So we will go back to lab and do some variation on the pressure.
Yeah.
Okay, clear enough. Thank you.
Thank you,
Professor Hidetaka. And we have a question for Professor Suzana, Yusup. What do you think? So the question is like, if we make our research as a candidate for the industrial scales, it's mean like we are introducing a new technology to the people. What do you think is the main challenge for those kind of situation to make it happen? Sometimes we are proposing like the real fact is the membrane. We are proposing to the industrial of the water producer. We propose membrane can give you a more clearer water, a more pure water that can be consumed by the people. But some of them might decline is it is expensive. It is not a very usable compared to the conventional one. So what do you think about that kind of situation? Thank you.
Yeah, I think thank you for that question. I think it's I mean, if you talk to the industry, of course, like I mentioned, cost is a very cost factor, right? Because then we need to have analysis, from the perspective of return of investment as well, and then if you are proposing for the certain productions, I think a detail of this economic analysis to be presented. Then they, to me, then they will have a more holistic view. Okay, if given this kind of a product, okay, with these assumptions of the cost, and if this this so much of initial investment to be put in, and this will be the recovery for that. So I think this a business approach towards it. It's a different language when, yeah.
Mm.
So I think this is a challenge for us as scientists as we engage more in pushing their products, right, from the lab to the market to be, prepared and present in this holistic manner, I think. Yep.
Okay. So that means we need other people on that field to make it more convincing in that way.
Yeah.
Like we ask some economic people to. Okay.
Yeah. Yeah.
Okay. Fair enough. Thank you
Yeah.
very much for your answer, Prof. Suzana. And we also have another question for Associate Professor Kawakita. This one is coming from Taufik. Is from chemistry department.
Okay.
Okay. So maybe his research, I think, in the same field as you in the microalgae harvesting. So he asks, we know that membranes for microalgae harvesting have problem with membrane falling.
Mm-hmm.
Okay, what is the solution for the membrane in your research on the falling problem? Is it just the cleaning method? Thank you. Or maybe he is asking more detail on the based on the previous question. Yeah.
Yeah. The question. So the backwash and cross flow rate is critical for the recovery of the microalgae. And yeah, that's it.
So do you think the physical treatment is enough for microalgae? Because some of the membrane are using some chemical to wash the falling.
Yeah. So by the chemical treatment, the structure of the microalgae will be destroyed. Yeah. So firstly, we should harvest the pure microalgae without destroying the structure. So we do not want to use chemical. So we firstly select the physical treatment.
Okay. Yes, because the microalgae itself is relatively bigger than the other membrane application, right?
Yeah.
The size. Yeah. Okay.
Yes, exactly.
Okay. So we have another question for Prof. Suzana Yusup. Here you have a lot of examples on your case. So we are interested in the single-step activation process. Here is for the activated carbon. The precursor you said palm kernel cell or PET scope binary. So the question is, you're activated by physical process, right? By CO2 activation. So based on your experience, which is have a more benefit between the chemical and physical activation for the carbon active carbon.
Yeah. Right. Thank you for the questions. In our studies, right, we have also do a comparative approach, right? What happened if we do a chemical treatment as well as when we do the innovative in terms of one-step activations using CO2. So we see the performance is different in terms of the quality. So this is at the end again back to the applications that you are targeting, right? Because then you have to outweigh, right? If you do this chemical treatment, then you need to know later how to manage the environmental, the waste from there again, right? So at the end of the day, like I mentioned, the holistic process plant approach still need to be done, right? So in the case where we use CO2 utilization, so there's a trade-off in terms of the quality, right? But then we the winning point is that you don't have to manage the waste. So it's not a direct question when we try to upscale technologies from the lab to the pilot plant. So as I mentioned, we need to have all these factors, the waste management, the supply chain, the cost. So these have to be considered in integrated manner.
Sure.
Right. Yeah. So yeah, that's my feedback.
Okay. Thank you very much for Suzana. Okay, for you guys, if you have another question, you can ask directly to our experts here by raising your hand. Okay, so here the question for Associate Professor Kawakita.
Yes.
On your slide, you show us about the microalgae cultivation. So based on my knowledge, if I'm not mistaken, the approach for the microalgae cultivation is there are two, like open pond and closed pond. So, but if we are doing in lab, it is hard to do the open pond because it needs a lot of area. So how your group cultivate the microalgae in the lab? Maybe you can give some insight to us.
You mean that in the, I'm not sure your idea, but in the case of the real application, your question is about the real application?
No, just in lab first. In lab.
In lab.
In laboratory. Yeah.
Yeah, we can make some simple experimental setup, pump and pressure gauge, and porous flow fiber membrane is set it like here is a porous flow fiber membrane, and some water is permeated by the pump, and pressure gauge is set at the second point, and we can set the pressure as a constant to make a cross flow. And some effluent is out from the porous flow fiber membrane. Very simple, like just like not Professor Suzanne's plant, much different to the very, I'm not sure, just like infancy, very low level plant, but we can get some data from that.
Okay,
thank you.
Hope it answer for the one who asked. Okay, a last question for Professor Suzana Yusup. So you are giving us a lot of process intensification. Based on your experience, how or when can we say that our process have optimized the existing one? I mean, what aspect can we look at if we propose some method or something that it will give a better understanding to the existing one? Thank you.
Yeah. Thank you for the questions. I think because when we link up the process optimizations and intensifications to find the optimum points where it falls, right? So there's various approach there. So among others, you can have the examples, Taguchi approach there. Okay, where they
That's
optimize,
very
very familiar, especially for the manufacturing plant. Yeah, they want to minimize utilizations of the fixed stock. At the same time, they want to optimize the time. And then there's also other approach there. Depends on there's I forgot. There's also you can compare that like the conventional one where they have one step at a time, right? So from there you know that when you do the optimization, it helps you a lot, in terms of the levels of the variables that you going to do, and also the number of variables that you will obtain. So difference on this approach of the optimizations, process optimization, then it will you will see the difference and where the optimizations point fall, right? And then once you have done, you follow all the arrays there. At the final stage, you need to reconfirm again, okay, the point where your optimized point fall. This is where you start comparing, okay, in reality, the models and the experiment, there you know that the variations of your approach for the optimizations, right? Yeah.
Okay, thank you very much. So a lot of aspect needs to be considered, I think, for the scale up. Okay, thank you very much, Prof. Suzana, for your kind answer. Okay, if there is no other question from our participant, I think we call it a day for today's session. Once again, I would like to thank to our spectacular speakers today, Professor Suzana Yusup and Associate Professor Hidetaka Kawakita,
Thank
for
you.
very interesting lectures in today's series. And I would like also to thank to all of the participants who have been actively in this session, giving some questions to our speakers, and so we can learn together in this session. And I will give back to the MC of this session. Thank you very much. See you.
Okay, thank you very much for Professor Suzana and also Professor Hidetaka for an excellent lecture today. And also thank you for Dr. Triyanda Gunawan for conducting this amazing session. And please give applause to our speaker and moderator using Zoom reaction feature. Okay, so furthermore, we would like to present a certificate awarding to our speaker and also our moderator today. Okay. So the first certificate for Professor Suzana. And then,
Thank you.
and then the next certificate. Okay, the next certificate, Miss Fifi. Okay, the next certificate is for Professor Hidetaka. Okay, I think there's a bad connection in here, Miss Fifi. Okay.
Miss Oche, would you like to redo it? We would like to redo it because of the bad internet connection.
Okay, wait a minute. Okay, okay then. Okay, Miss Nastiti, could you please?
Yes, please. Now.
Okay. Again, first certificate for Professor Suzana.
Thank you.
And yes, and the second certificate is for Professor Hidetaka. And finally, for our moderator, Dr. Triyanda Gunawan. Okay, then once again, thank you very much for Professor Suzana, Professor Hidetaka, and Dr. Triyanda for your availability on today's guest lecture series. We believe that your lecture will be useful for all participants in the present, even in the future. Now, before we end our lecture today, I would like to invite all participants as well as our honorable speaker and moderator to take a group photo. So to all participants, please open your camera and I will count so we can take a photo together. Okay, I see there is 2 pages opening their camera. Okay, I will give you 5 seconds to prepare your own self. Okay, then. For the first page, in the count of 3. 1, 2, 3. Okay. Second page. 1, 2, 3. Okay, then. Okay, then. Now we've finished our group photos. So then for the participant, please fill the feedback form through the link bit.ly/feedback_GLS that you can also see in the Zoom chat room. And the deadline for filling the feedback form is 1 hour after we finish this session. We want to remind you to the participant who will get the stamp are the participant who come join in time, join this event until the end, and also fill the feedback form. Yes. Okay, and then we also have an interesting topics in next week's GLS on SDGs. Okay. Okay, as you can see, we have about 3 topics in here. There is how artificial intelligence will change the future, communication and artificial intelligence that will according to SDGs number 9. And then also in the stream view, we have simulation of train dynamics about SDGs number 9 too. Okay, then, so that's about our GLS on SDGs next week. And finally, we reached the end of today's guest lecture series, and we sincerely apologize for the mistakes that we have made in presenting as a master of ceremony and a committee. And again, thank you very much for our honorable speakers, moderator, and all participants for attention and your cooperation. We hope to see you soon in other occasions and events in the future. And don't forget to follow our social media on Instagram at ITS International Office and also Facebook at ITS International Office, and keep updated of our programs. So that's from me as a Master of Ceremony and Committee. Good afternoon and wassalamualaikum warahmatullahi wabarakatuh. Thank you, everyone.
Thank you. Bye-bye.
Thank you.
Big thanks to Professor Suzana Yusup and also Professor Hidetaka Kawakita and also Dr. Trianda for today's very interactive and amazing session in GLS on SDGs. On behalf of the committee, thank you so much. See you around, and also permission to end the session in 3, 2, 1.